I think we should be live at this point. Need to double check that. Hmm. Hello, hello. Actually, probably should have checked the audio before starting. Anyway, we are live. Just confirmed it. All right, so this is going to be um, a short, I guess, study session. um, just really gonna read through an article that I came across. I think it was yesterday, and yeah, I mean, I've read a couple of things from this blog post by Lorin Hochstein. I hope I'm pronouncing that right. Really solid stuff, usually. Um, I saw the title of this and I figured that'll be another really interesting article to go through. So yeah, I think that's what we're gonna do. I think that's about all the intro we really need. I think the title kind of speaks for itself, as in tells us what this is, what we can expect in terms of the content. Um, yeah, let's just jump right in. All right. Amazon's recent announcement of the spec-driven AI tool, Cairo. And I mean, if you haven't heard of Cairo, it's oh, okay. Uh, it's the new ID that Amazon released. Excuse me. It's supposed to be, a competitor to tools like Cursor and Lovable and I guess Bolt. But the angle that they are taking is really, this spec-driven uh, angle where I mean, I haven't tried it myself, so I don't know how much of this is actually really um, concretely applied to the product. But it seems like the angle that they're going with is instead of just eagerly just generate a bunch of code uh, right off the bat, it seems like they've built the IDE to put emphasis on the process of just really, I guess, uh, writing the specs for the system that you're trying to build. Um, which is I think that's an interesting road to take. So I guess before I continue, I need to double check some things in OBS. Um, I'm using OBS on a different account than the one that I usually use um, for streaming, and so I'm actually not sure that the sound is any good. I mean, I hope it is, because Um, Otherwise, this will be, I mean, it will be a shame. Because, I mean, I'm not going to stop streaming now to figure that out. Um, anyway, I mean, yeah, I think something is off. Good. Oh well, let's just power through this. I don't want to not do the thing that uh, I actually want to get done. So let's just keep going, and hopefully the audio is just good enough. Otherwise, maybe I'll just, I don't know, do a redo, a recording. I mean, a re-recording or a restream, but probably not. Okay, so Amazon's recent announcement of the spec-driven AI tool, Cairo, inspired me to write a blog post on a completely unrelated topic, formal specifications. In particular, I wanted to write about how a formal specification is different from a traditional program. It took a while for this idea to really click in my own head, and I want to motivate some intuition here. Okay, so so formal specifications uh, is different than uh, than a program. Just taking notes here. Is an idea that may take some time to internalize, but the distinction matters. That's basically what I'm getting from that. Let me make this a little smaller. So I actually have Claude here on the side just in case I have questions. But I think I'm just gonna stretch this out like this for now. Three, just like that. Okay. Yeah, okay. In particular, there have been a number of formal specification tools that have been developed in recent years which use programming language like notation, FISB, P, plus cal and quint. I've heard of all of those. I think these notations are more approachable for programmers than the more theoretic notation of TLE plus. Yeah, I will agree with that. Recently I did a read through of the Raft local in TLE plus, and it does get gnarly. Takes some getting used to, definitely. But I think the existence of programming language like formal specification languages makes it even more important to drive home the difference between a program and a formal spec. So uh, yeah, I think this is, I mean, the point is pretty clear here, straightforward. As spec, okay, I guess as specification languages, um, adopt a more programming or programmer programming, I'm just gonna use what he said. Language lack syntax. It matters not to lose track of the fact that a spec is still not a program in the traditional sense. Okay. Summary of this post. Okay, I'm actually gonna just write that. A program, a list of instructions, a formal specification is a set of behavior. I think that's a succinct way to put it. All right, so I'm gonna put this as introduction, and what kind of software do we want to specify? Generally speaking, we can divide the world of software into two types of programs. There's one time when you give the program a single input, sorry, and it produces a single output and then it stops. I think for the most part, I think we tend to call that scripts or jobs. I think like when you think of a script or a job, it's usually a one and done, like straightforward, beginning and end. The other type is one that runs for an extended period of time and interacts with the world by receiving inputs over time and generating output over time. Yeah. And these types of programs lend themselves more so than the other type to, the idea of state machines. Okay. In a paper published in the mid 1980s, the computer scientist David Harrow, developer of state charts, and Ami Pnuli, the first person to apply temporal logic to software specifications, made a distinction between programs they call transformational, which is the first kind, and the other, which they call reactive. Two types of programs. It's nice to actually have a proper ways to refer to those kinds of programs. Transformational, say versus reactive. Former is more of a one and done type. Okay, so shut that. Where given some input, you get an output and the program terminates. Ladder is continuously running with and receives is continuously receiving inputs that it processes over time, from which I continuously, is continuously receiving inputs from which it produces or yields outputs over time. Okay. A transformational. There's a black box. There's a black cactus. Interesting. Okay. I should probably add this source. Um, by the way, I'm just typing this as a little just text file, so there's nothing like fancy syntax or anything. It's just a blank like text thing, because I figured it just, I don't know, it's just nice to just write without caring too much about presentation. At this point, it's just really reading and writing at the same time. I find that it's you're likely to be more engaged with the content. Like it's less of a passively, or reading passively. Is that, am I saying that right? Like, you're more engaged, you're more likely to ask questions, look up things, and now when you have something, a tool like, whether it's ChatGPT or Claude or whatever, where you can ask questions too. Anyway, okay, so a compiler is an example of a transformational tool. So let's put example compiler. The obvious example here is a database or a game engine. An example of the second time is the flight control software in the airplane, which runs continuously, taking inputs and generating outputs over time. In my world, we call services. In my world, we call services algorithms. Doesn't matter, not really. Service algorithms for reactive systems. There are long-running programs that receive requests as inputs and generate responses as outputs. The specifications that I'm talking about here apply to the more general reactive case. Yep. Because I think from a formal specification, I don't know, maybe this is a gross oversimplification, but I think reactive systems are probably more interesting. And by interesting, I mean challenging to write specifications for. All right, a motivating example. Actually, I'm just gonna do this. A motivating example. Let's consider the humble counter as an example of a system whose behavior we want to specify. Let's describe what operations I want my counter to support using Python syntax. Okay. Let's say let counter let's just do this. Fun ink none get. I mean, I know I don't have to write this, but you know, part of the process of, again, just being actively engaged with the material. Okay, so we have the counter. An example will be sequential to keep things simple, but all of the concepts apply to specifying concurrent and distributed systems as well. Know that implementing a distributed counter is a common system design interview problem. Behaviors. Above I just showed the method signatures, but I implemented this counter and interacted with it in the Python REPL. Here's what that looked like. Okay, so increments. Okay, that makes sense. People sometimes refer to the sort of thing above by various names: a session, an execution history, and an execution trace. The formal methods, people refer to this sort of thing as behavior, and that's the term that we'll use in the rest of this post. Specifications are all about behavior. I think what I want is, I'm not gonna actually type things. I'll use the REPL because these are pretty straightforward things that are happening here. So I'm gonna do this 3 times. Cnc and well, I don't know why I'm doing this to myself. I have to type this. Reset. But now I don't like that. How about that? So you get C reset. So that should take us to 0 again, I believe. And then we do a C get. That should give us a 1. Just for sanity's sake, let's double check. So we said 0 and 1. Okay. Okay. The above is what's referred to as behavior in the context of no specification. Okay. Sometimes I'm going to draw behaviors in this post. I'm going to denote a behavior as a squiggle. Okay, to tie this back to the discussion about reactive systems, you can think of method invocation as inputs and return values as outputs. The above example is a correct behavior of our counter, but a behavior doesn't have to be correct. A behavior is just an arbitrary sequence of inputs and outputs. Here's an example of incorrect behavior for our counter. Okay, so increment. Yeah, okay, yeah. Clearly this is wrong. We expected get method to return 1, return 4, so that means there's a bug somewhere. Okay. So there was something that was mentioned here that I wanted to note. Okay, yeah. Something about a behavior need not be correct. It's just an arbitrary sequence of inputs. All right. Specifications and behavior. Ooh. Okay. And behavior. What we want out of formal specification is a device that can answer the question. Here's a behavior. Is it correct or not? Here's a behavior. I like that quote. Is it correct or not? All right. That's what a formal spec is for a reactive system. A formal specification is an entity such that, given a behavior, we can determine whether the behavior satisfies the spec. Correct is equal to satisfies the specification. Given a behavior, we we want to know if the spec. Wait. What about there? Given a behavior, you can determine whether the behavior satisfies the spec. Okay. Just trying to reword this for my own muscle memory. That's one way to put it. You have one fidelity between relative to the spec. I don't know. Does that sometimes make sense? Relative compared as one fidelity. It's good enough. You can correct it later. I'm not happy with it when I go through the notes. Once again, a spec is a thing that will tell us whether or not a given behavior is correct. Okay. Guess I cannot. This tells us whether the behavior is correct or not. Okay, spec as a set of behavior. I feel like I should make this a subheading as a set of behaviors. I depicted a spec in a diagram above us, literally a black box. Let's open the box. We can think of a specification simply as a set that contains all the correct behaviors. Now, the correct processor above is just a set membership check. All it does is check if a behavior is an element of the set spec. Okay. It boils down to checking if oh, okay. A spec, well, it boils down to checking that a behavior is an element of the set of correct behaviors as not illustrated, as I guess modeled or specified by the spec. Note that this is a simplification. This is what a formal specification is in a system like TLA+. It's just a set of behavior, nothing more, nothing less. Okay, so describing them. Well, you know what, I'll just keep going. You're undoubtedly familiar with sets. For example, here's a set of the first three positive natural numbers. Here we describe the set by explicitly enumerating each of the elements, while the idea was behind a set of behavior is simple. Actually, describing that set is trickier. That's because we can't explicitly enumerate all the elements of the set like we did above. For one thing, each behavior is, in general, of infinite length. Taking the example of our counter, one valid behavior is to just keep calling any operation over and over again ad infinitum. True. This is a correct behavior for our counter, but we can't write it out explicitly because it goes on forever. It is tricky to formalize this set of behavior to succinctly enumerate. I'm gonna put in all the set of behavior that we intend on verifying, on checking. No, that yeah, because you are specifying the overall set of behaviors, but that doesn't mean that like, but then that becomes useful because precisely because you're trying to then um, evaluate a given behavior. I think I understand right. What was I here? Enumerate the set of behavior that it's really thrown as enumerate the set of behaviors that uh, we want to um, uh, use to model the reactor system. Yeah. The other problem is that specs that we care about typically contain an infinite number of behaviors. If we take the case of a counter for an infinite correct behavior, we can always generate a new correct behavior by adding another increment. Yeah. So even if we restricted ourselves to behaviors of a finite length, if we don't restrict the total length of a behavior, if our behaviors are finite but unbounded, like natural numbers, then we cannot define a spec by explicitly enumerating all the behaviors of the specifications. And this is where formal specification languages come in. They allow us to define infinite sets of behaviors without having to explicitly enumerate every correct behavior. Um, the goal of the use of specification, no, let's just keep it simple. Specification languages are tools that help us with expressing the sets of behavior. We are interested in or given system. Describing infinite sets by generating them. Mathematicians deal with infinite sets all the time. For example, we can use set builder notation to describe the infinitely large set of all even natural numbers without explicitly enumerating each one to k such that k is in the set of natural numbers. The example above references another infinite set. Yes, the set of natural numbers. The set of, yeah, okay. Literally. Okay. How do we generate the infinite set without reference to another infinite set? One way to define the set of, one way to define the set by describing how to generate this set of natural numbers. Wait. Oh, how to generate, sorry. It's getting late. Okay, let's start over. One way is to define the set by describing how to generate the set of natural numbers. To do this, we specify an initial natural number, either 0 or 1, depending on who you ask. I don't know, I think I've always just, yeah, I don't know. I don't think it was ever. I guess my math is foggy at this point, but I just don't recall. Um, yeah. Anyway, just gonna move on from that. A successor function for how to generate a new natural numbers. Natural number from the existing one. Okay. This allows us to describe the set of natural numbers without having to enumerate each one explicitly. Instead, we describe how to generate them. If you remember your proofs by induction from back in math class, this is like defining a set by induction. Yep. Is there anything to note here? Uh, I don't think so. I think that was, yeah, I think that was good. That's fine. I don't think I have anything. I'm okay not necessarily putting anything down for that. Specifications as generating a set of behavior. A formal specification language is just a notation for describing a set of behaviors by generating them. In TLA Plus, this is extremely explicit. All TLA Plus have two parts. Init, which describes all the valid initial states, and next, which describes how to extend an existing valid behavior to one or more new valid behaviors. Here's a visual representation of generating correct behaviors for the counter. Yeah, so these will be the actions that can be taken. And next, essentially, pick any one of them, and you basically branch out from there. Note how in the case of the counter, there's only one valid initial state in a behavior. Wait, what? Oh, okay. Yeah. All right. Yeah. I mean, the initial state is just 0, right? And it's the correct ones. All of the correct behaviors start the same way after that when generating a new behavior based on a previous one. Whether one behavior or multiple behaviors can be generated depends on a history. If the last event was a method invocation, then there's only one valid way to extend the behavior, which is the expected response of the request. If the last event was a return of the method, then you can extend the behavior in 3 different ways based on the 3 different methods we can call on the counter. So what they're referring to is basically once you've basically picked an action, so let's say in this case we go with get. From that point on, like at least the first layer after that is just the responses that you get from the actual call. But then from there, you can, I guess, respawn the branch, so to speak. Okay, let's see. Okay, the init next pair describe all of the possible correct behaviors of the counters by generating them. Okay. Not well, see if I can copy C counter in this state transitions. Oh no, behaviors here. Yeah. Okay. No determinism. Okay, so one area where formal methods can get confusing for newcomers is that the notation for writing a behavior generator can look like a programming language, particularly when it comes to non-determinism. When you're writing a formal specification, when you're writing a normal formal specification, you want to express here are all the different ways that you can validly extend this behavior. Hence, you get the branching behavior is on it, right? Okay, so hence you get that branching behavior in the diagram in the previous section. You are generating all of the possible correct behaviors in a formal specification. When we talk about non-determinism, we mean there are multiple ways a correct behavior can be extended. That includes all of the different potential inputs that we might receive from outside. I like the last part there. We're actually not gonna have its own section. I'm just gonna say I like that quote. Well, that phrase or that set of words, whatever, is about extending a correct. Did I put that in quotes? Probably. Is about extending a correct behavior along multiple. Specifically, an example of this will be from this point on, like, once you reach this point here, this is a correct behavior. And then from here, you are exploring different paths. You are extending this, the correct behavior up to this point. You're extending it by these possible paths, which, can lead to other correct behaviors. Okay. Sorry, okay. On the other hand, so we are here. Okay. On the other hand, in a computer program, when we talk about code being non-deterministic, we mean we don't know which path the code is going to take. Yeah. Like, yeah. When in formal spec, I mean, it's just that like there's a predetermined set of paths You just don't know exactly which one will be taken, because any one of them can be. And yeah, but for a program, it's much more murkier. Yeah. On the other hand, in a computer program, when we talk about code being non-deterministic, we mean we don't know which path the code is going to take. In a programming world, we typically use non-determinism to refer to things like random number generation or race conditions. One notable area where there are different is that formal specifications treat inputs as a source of non-determinism, whereas programmers don't include inputs when they talk about non-determinism. If you said user input is one of the sources of non-determinism, a formal modeler will nod their head and a programmer will look at you strangely. Really? Have I listened to what's his name? Jordan, is it Jordan Cave from Tiger Beetle a little too much? No, it's not Jordan Cave. Oh, sorry. I'm just gonna put Jordan K and Tiger Beetle. Forget it. Grief. Okay, Jordan Grief. No, not even Jordan. Jesus, what's wrong with me? Joran. Grief. Ah, I'm sorry, man. I'm sorry. I should know this. I've watched so many of his talks. Because I mean, based on his talks, he makes it very clear often that yeah, user input is a source of non-determinism. Unless I misread. Well, I guess it's about context, really. Because, yeah, if you are already thinking in terms of deterministic simulation testing, then, I mean, you're closer to the mental models of formal specification modelers than you are to a programmer, like in terms of, you know, the optics or whatever. Um, so yeah, from a deterministic simulation testing standpoint, I think it's just a given that you treat your user input as a potential source of non-determinism, and then you act accordingly as you're designing your simulation. Okay, what do I want to write down here for this? Uh, in formal specification, user inputs are most definitely considered sources of non-determinism. This is not a given. From a um, traditional program, programming, um, frame, framing, less. No, I'm just gonna use less. I think that kind of summarizes the big idea here. Yeah, okay. Properties of a spec sets of behavior. I've been using the expression called behavior and behavior satisfies this satisfy the specification interchangeably. However, in practice, we build formal specifications to help us reason about the correctness of the system we are trying to build. Just because we've written a formal specification doesn't mean that the specification is actually correct. Indeed. Uh, always watch out. And I mean, this is, if you've read it or known anything about formal specification, you know that that's like one of the main things that you should always be on the be wary of, which is, yes, you have a formal spec, but is it actually useful? Are you actually capturing the right properties of the program? Because otherwise, your spec is useless, and it could actually be worse. Like you can be worse off basically by having a specification that is, for all intents and purposes, a faulty one. Um, so always uh, be uh, alert. Oh, what am I typing? After be alert to the fact that uh, a specification uh, needs to be correct. Needs to yeah, needs to be correct in order to be useful. Um, this can be tricky to get right. It is a big part of the challenge of producing specifications. I'm still awake. I'm still awake. All right. The most frequent tactic people use to reason about the formal specification is to define correctness properties and use the model checking tool to check whether the specification conforms to the property or not. Here's an example of a property of for our counter. The get operation always returns a non-negative value. Yep. Okay, those are, so it's increment, get, and reset. Okay, just wanted to make sure there was no decrement in there. Also, when you increment, we know that it's always by, at least in this context, without any more, although you could argue without, maybe I missed where he mentioned this specifically, but uh, I think we kind of all assume that here increment means you're adding +1. Um, Now, if you want to start being very specific and stickler, you could make the case that, well, actually, no, we don't necessarily know that. The increment could actually have some sort of random selector that either increments by 1 or increments by 2 or increments by 7, depending on the position of the moon relative to the sun. As ridiculous as that sounds. Um, and that's the point of specifications. It forces you to recognize the, or at least be be aware of the fact that until you've actually thought about some components of your system, there are likely some unknown unknowns. Um, that you need to, I guess, reveal as part of the, as part of the process of producing these specs. Basically forces you to really think about what does it mean for a given program to be correct and to do the thing that it's intended to do. What are the assumptions that are being made? Um, yeah. Uh, okay, so however in practice we be formal spec to help us, just because we've written a formal specification doesn't mean that the specification is actually correct. That means that we can't treat the formal specification that we built as the correct description of the system in general. Oh, I already read this actually. Okay, so use the auto checking tool. We know that. So I think TLA Plus uses TLC, if I remember right, and I mean Z3 is a pretty uh, prominent one that people use. Um, Anyway, so here's an example of a property. Yeah, okay, so we made it here. Let's give it a name, the non-negative gets property. Our specification has this property. We don't know for certain it's correct, but if it doesn't have this property, we know for sure something is wrong. Yeah. Right back. Almost there. Right, okay, was there something here that I may want to note down? Um, uh, the process of constructing specs involve um, what's the word I'm looking for? Uh, Not discovering. Lifting. Lifting out. No. What's like involve I feel like I have the concept. The word is just not landing. The process of considering specs involve declaring the correct desired properties of the system being specified. I think that's straightforward enough. Okay, like a formal specification, a property is nothing more than a set of behaviors. Here's an example of a behavior that satisfies a non-negative property. Yeah, here's another one. No, that the second one. Wait, let's see. C get, C increment, C get. Yeah, I mean, that's wrong. Okay, so know that the second know that the second wrong probably looks wrong to you. Okay, the second one. Okay. Know that the second one probably looks wrong to you. We haven't actually written out a specification for our counter in this post. But if we did, the behavior above will certainly validate it. That's not how counters work. On the other hand, still satisfies the no negative gets property. In practice, the set of behaviors defined by a property will include behaviors that are not in the specification as depicted below. Okay. This is a property, this is a spec. Spec that satisfies a property. When we check that a spec satisfies a property, we are checking that spec is a subset property. We just don't care about the behaviors that are in the property set but not in the spec set. Okay. What we care about are behaviors that are in spec that are not in property. What we care about are behaviors that are in spec. That are in spec that are not in property. Okay. That tells us that our specification can generate behaviors that do not possess the property that we care about. Okay. This picture actually really helps simplify the thing. Yeah, okay. Let's say it's possible for the set of behavior um from a property to not be to not belong. Wait, no. Uh, uh, we think it's more straightforward to just say we care about uncovering sets, I guess, behaviors that are in the spec, but not uh, uh, by spec here, I think we understand it's the set of behaviors of the spec. Okay. They're in a spec, but not part of um, a property behaviors. May have to rephrase this later. Okay, so consider the property that always returns a positive number. We can call it all positive gets. Wait, like, this is where being specific matters. Do we mean natural number or, you know, integers? Decimals, real numbers. Mm. Note that 0 is not considered a positive number. I always found that a little weird. I think more specific. Wait. Wait then. Know that for specificity, it is sometimes said, you know, the set of non-negative numbers. I think that's to explicitly exclude 0 sometimes. Don't quote me on that. I'm not gonna look it up right now. Assuming our counter specification starts at 0, here's a behavior that violates the all positive gets property. Yep, right off the bat. All right, thinking in sets. 1 hour. Oh, almost there. Okay. Thinking in sets. When writing formal specifications, I found that thinking in terms of sets of behaviors was a subtle but significant mind shift from thinking in terms of writing traditional programs. Where it helped me most is in making sense of the errors I get when debugging my TLA plus specifications using the TLC. Yep, TLC model checker. After all, it's when things break. It's when things break. No, okay. when things break is when you really need to understand what's going on under the hood. And I promise you, when you write formal specs, things are going to break. That's why we write them, to find where the breaks are. All right. And that was solid, as usual, from Mr. Lorin. And we are going to end here. It's quite late. I don't think there was a whole lot to say as closure. Yeah, so think of specifications as set of behaviors. Definitely be thoughtful about the the properties that you are looking to validate, I guess, about your system. What else? I think just oh yeah, it was nice to have a like some sort of clear definition of, you know, the two types of programs that uh we deal with, transformational versus reactive. Those are useful terms to be more specific when, you know, thinking about programs and specification in general. Um, yeah, okay. Well, I'm gonna end it here, and I'll see you around in another stream.